it goes through the homogeneous. Okay, what we did last time, the homogeneous ones. So that's what the test goes through. So, but not the exact, not the we started the partial derivatives and all that. That's not on. That's the exact stuff. But before that, okay, would be for the test. But anyway, kind of picking back up here. So me back here real quick. Okay, so this is like section 2. I think it's 2.5 continued here. Okay, and we'll just kind of start with the problem here, kind of dive right in to it. Let's see, but kind of in a nutshell, just real quick again. You don't have to write this down, but kind of from last time, right? We had like this here: if f of x, y is equal to c, okay, then this is true here. Okay, like this. Okay, so if you have this here, then this is true. Okay, and basically we're trying to solve equations look like this here. Okay, but we have to figure out if what's here is really a partial derivative or not in some of these. So, so basically here, let's just start with the problem. Let's see how to solve this here. Okay, so let's say we got this one. Plus a little bit wordy here. Okay, so let's see how to solve this. Now remember what this is. This is really it looks kind of weird here if the dx and dy separated out like this, but it's really just, don't write this down, but it's just the same as this, really, right? It's like, it's like you can divide through by the dx, and, you can even move things around here if you want, but this is like the differential equation here. You can take this, move it over the other side, or, and then divide by this, whatever. Okay. But for purposes of solving it using this method, right, you want to, you write it in this form though, right? So you write in this form here to start. Okay. And this is like the m. Right, this is the m, and this is the n. Okay. And basically what we've got to do here first, we got to try and figure out is m equal to f of x for some function. It's like a question mark here for now. I'll put a question mark there. Okay. And then, so we got to figure out that first of all. Are these, is this partial derivative of some function here, like that? And there's a test for this, for the exact part. Okay, so a test for exactness. You want to find this here. You see, is m sub y equal to n sub x? Okay. And so, okay, so that's the test for exactness here. Okay, now, let's see. Okay, so you need to find m sub y here, right? So let's find those separately. So m sub y, okay, equal to what then? So you take the partial here, the partial of this in respect to y. Okay, so how would that go then? Partial respect to y for that would be what? That'd be, well, what would it be? So partial respect to y? Yes, cosine y minus sine x. So that's partial respect to y for that one. Okay, now we'll compare that to, say, partial of n with respect to x. Okay, so, and you do the same, so partial of n with respect to x here would be what? That would be negative sine x and then plus cosine y. Like that. And notice these match, right? These are actually the same thing here. Okay, so they match. So, they check out, right? So I'll just say, I'll write this, maybe m sub y equals n sub x. I'll put a check mark, right? So those match there then. Okay. Now, basically what we're doing there, when you find those partials like this, it's like you're finding, if this is like the first derivative, partial respect to x, partial respect to y. Remember how you said the second partials have to match? When we did second partial derivatives, the mixed ones, they match. And that's what you're saying here is, yeah, actually the second partials match, right? So that means actually this is, yeah, so you have to have that condition there. If you have that condition, then it turns out this is exact then. Okay, so now what you can do, now that means then the M really is equal to F sub X then, okay? So we answer yes to that now. We get rid of that question mark there. Okay, so now we know that F sub X is equal to this then. Maybe I should say here, I'll say here so. Maybe we'll say so here. Okay. Okay. Right. So we have this here then. Now basically we're trying to figure out the f of xy now that would generate this. What has this as its partial here then with respect to x? Okay. So we have f of xy. Okay. And basically here now you do antiderivative with respect to x. Okay, so you treat the y like a constant. Okay, take antiderivative with respect to x. Okay, so that would be what then? Here, take the antiderivative with respect to x. Treat the y like a constant. So how would it start then? Yeah, it'd be x sine y. Okay, x sine y. Because again, if this is a constant here, okay, then it'd be that constant times x. That'd be the antiderivative then. Okay. Minus now over here then, this would be what? I'm going to pull the door. So you want to take the antiderivative here with respect to x. That one, antiderivative with respect to x. You treat the y like a constant. It's y, then there's going to be a sign switch in there or something. Yeah, y negative, they got a double negative here. So it'll turn them back positive, right? So plus y cosine x. So, okay, so we got then plus like that. Okay, so that's the antiderivative with respect to x there. Okay, now it's also possible then, right, for this function, then there could be another part here that's just purely a function of y over here. Call it, say, phi of y. I think the book calls it phi here, but like that. Okay, right. If you take the partial of this with respect to x, take partial with respect to x here, you would get this. Right? If you take the partial with respect to x, because this would drop off. Okay, so going backwards, right, it could be something like this then. Okay, now next thing then, we also know another thing here, right? The partial with respect to y has to be this here. Okay, so that's another thing we've got to look at. So what you do now here, this, now take the partial of this with respect to y. Okay, so partial with respect to y of this. Okay, what would that be then? So partial with respect to y would be, right, x cosine y. And the partial with respect to y here for that one would be, yeah, it's a constant, right? So just plus cosine x. Okay, we got that. And then over here, now this is an ordinary derivative here because it's just a function of y here, right? So plus, I can say phi prime y, call it like this, I guess. So you got that here. Okay, anything else so far? Now what? Now the other thing we know, so that's from taking the derivative, but we also know that f sub y has got to be what? It's got to be this expression up here, right? So it's got to be this thing here. So on the left side here, right, substitute in this on the left side here now, right? So you get cosine x plus x cosine y. And then minus y there. That's going to be equal to this then. Like that. Okay. Now, notice here at this point, a lot of things drop out, right? So on both sides, right? The cosines drop out. So basically here you just get what? Negative, right? These drop out here then. Well, yeah, they drop out on both sides. So you just get what? Negative y is equal to phi prime of y, like this. Okay, anything there so far? Now, that's kind of a key point here on this. If you get x's left here, if you're doing this and get something with x's left in it, that means it was not exact. Okay, so the method fails then, right? If you get stuff with x's left here, that's not right then, because this has to be a function of y only. It can't have x's and y's over here. So if you skip the test for exact, or if you skip this part here and go to do the problem without doing that, okay, this is where you'd run it. This is where you'd see it here. Okay, it would not work out right. So really, if you wanted to, you could skip the test part, this check mark part. You could skip that if you want and just dive right into it, and try this out here. But you'll get caught. You'll get stuck here then if it's not going to work. Okay, but you can do the test. It's okay to do the test first. But if you forget to do the test for whatever reason and just start doing the problem, you would get stuck right here because you have x's left in it. So, but okay, now at this point, now we've got phi prime of y is equal to negative y. Okay, maybe we'll write the other way. Okay, now you just do antiderivative here, right? So phi of y is equal to what? That is negative 1/2 y squared. Okay, plus well, you don't have to add a constant. You don't need to put a constant on it. So you get this here. Okay, and that is this part over here then, right? That's this part is this. Okay, so then the f of xy so we got right, so we got I'll say it this way. So that means f of xy is equal to x sine y plus y cosine x minus 1/2 y squared. Okay. So that means then, now that's our f of xy then is equal to this, right? But back in the beginning though, I remember it's all kind of based on this thing right here. Okay, so now we got the f of xy now. So the solution then is this then. It'd be x sine y plus y cosine x minus 1/2 y squared equals c. Okay, because this is the fxy part. Fxy equals c is the implicit solution then. Okay. So, and we'll just leave it here then for this one. But in principle, I guess it's kind of difficult to do here. But if you really can't. It's pretty much impossible to solve for y here. Okay, so you just have to leave it like this. These would be your curves here then for that, because that'd be the implicit solution here. Okay, so any questions on that? How that went? We'll just do a couple more examples here, but that's basically the idea of it there. Let's see. Yeah. Yeah, we'll do one next here. Yeah. Yeah, if we could do initial value problem, we'll do one here. So, okay. So, actually, the initial value problems are kind of easy almost with this one in a way, because your c is right here on the end. So if you have an xy pair, you can plug it in and get the c right away. So it's kind of ready to solve for it. Now, if we want to solve for y, then after that's kind of a mess. But if we're just going to c and stop, yeah. But, okay, anything on that one? Well, I got one more example here to do, but it's very, very systematic. Like once you do a couple of them, it's kind of tedious, but my notes are a mess. Okay. All right, so I'm just going to solve this one now. Oops. Okay, so I'm going to solve this one here. Okay, and basically the same idea here then on this one. You could do the test first to see if it's exact or not. I guess I'll do that. So m sub y, right? This is the m, and this is the n. Okay, so you take the partial of that in respect to y. And how might that go then? So I guess the e to the x comes down. It's a multiplier, right? And then that would be, what, 2y here? Is that right? I think that looks right. That's m sub y. Okay, then n sub x is equal to, I get 2y is like a multiplier there. And then the rest would be what then? E to the x, right? So e to the x. So it checks out, it's exact. Okay, so now we can, this is like our f sub x over here then. And this will be our f sub y. Okay, so maybe you don't have to do this, but I'll put the little question mark here, just kind of remind you. So we're trying to see, trying to see if that'd be true there, those two things. So that we checked out, that would be true then. Because the second part, the mixed seconds match now, the mixed second derivatives match. So got that. So now we go about finding the f x y then. So we had, now by the way, you could integrate either of these first here. You could do this one first. You could do f sub y first, whichever is easier. Okay, they're about the same here, but I guess it's a matter of habit. I'll do f sub x first. Okay, but you could integrate either one. If you're stuck on one, try the other. And so f sub x, that's this up here. So e to the x times y squared minus 3 plus 1. Okay, so then f of xy. Okay, so if I do this one here first, and I derive with respect to x, so you treat y like a constant. So that would just be, I guess it'd be like, well, I'll write the constant first. Y squared minus 3 e to the x plus x, like that. Okay, with that one, anything there so far? And then also, I forgot, plus possibly some function over here of y, like that. Okay, now next thing then, I take the partial of this with respect to y. Okay, so then f sub y would be equal to, oh, one more thing I forgot, and this one I forgot to mention. That we have an initial value problem here. Let's say y of 0 is equal to 1. I forgot to write that down in the beginning. So y of 0 equal 1, let's say there. Okay, but f sub y then, and I take partial with respect to y here. So what, that'd be like e to the x is a multiplier, and that would be 2y then, right? Okay, plus, yeah, phi prime y, like that. Okay, so you have this here. Now the f sub y then, we know it's got to be what? It's going to be 2y times e to the x plus 8. So we got 2y e to the x plus 8 equals, this is 2y e to the x, okay, plus phi prime y. We got this here then. And, oh, I lost my train of thought. What am I doing? Okay, I took the, see, oh, yeah. So we had, right, this up here. We put it on the left side. Okay, and now basically here, if you distribute this out here now, you get 2y e to the x plus 8 equals 2y e to the x plus phi prime y. And just like it has to happen now, these have to cancel. Get rid of the y's here. You see something? Did I? It probably is. Yeah, you're right. You're right. Thank you. Yeah, that. Okay, and now those two terms cancel, right? The left and the right there. So you just get 16y equals phi prime y. And again, this is a function of y only, which is good. Otherwise, it's a dead end. Okay, let's get this here. So then, so what, 5 prime y equals 16y. So 5y is equal to, that would be 8y squared. There. Like that. So then that's this part right here. So then we got our f of xy here then. Okay, so then the solution, it would be y squared minus 3 e to the x plus 8y squared equals c. Okay, so this is the f of xy right here. And then remember, the solution, it's equal to c then. Okay, those are the solution curves. Right, so we got that. Anything there so far? Okay, now this was an initial value problem here on this one, right? We had this condition. So there's actually like a bunch of different curves there, a bunch of different values of c, bunch of different curves on that. But we're interested in one of them here. And normally, I don't know, normally if you're going to do, well, it's so easy to get the c right here now. Sometimes if you're trying to get explicit solutions to solve for y, a lot of times you solve for y first and then put in and then figure it out. But it's so easy to get the c here right now that there's no reason not to. Okay, so just get the c here now on this one because we got the condition up there 0, 1, right? So let's get you the c here like that. Just substitute it in. So that is what? That's -2 plus 8 equals c. So c is equal to 6. Okay, so we get here then that y squared minus 3 e to the x plus 8y squared is equal to 6, like this. Okay, now, so this is the implicit solution here then. And sometimes you might want to solve for the y to get the explicit curve y equals a function of x. I'm going to do that here. Just sometimes in the homework, it'll say, you want to get y equals and then something. So I'll go and solve for the y here, get the actual function. This one you can actually do it. It's not too bad. It's a bit of a pain, but you want to solve for the y here. So if I solve for the y, and I'll be specific on a test or something. I want you to solve for the y or not in some of these. Okay, but we'll see. If I say find y as a function of x, or y of x equals or something. But anyway, if I go about solving it a little bit, I guess you'd have to maybe, I'll distribute here first. Okay, and then now what you would do here then, you would get the y squared by itself. So basically, move the non-y terms over to the other side. So you move those terms over to the right. Okay, so then you get like y squared e to the x plus 8y squared equals 6 plus 3 e to the x plus x, I think, like that. This is actually possible to do, really, because they're both y squareds here, right? Is it minus x? Yeah, thank you. Yep. Yeah, I get this. And now what you would do here is, how would you solve for y then? You could factor out the y squared. Okay, and then divide this then. Okay. Finally, take square root. Okay, and I'm going to write this just for a minute here. I'll put plus or minus here. So we take the square root, you get plus or minus in front of that. Okay, but actually, for this one, though, both of these are not right because we had that initial value here. When you take that square, you got to be careful at the plus minus. It's not really both of them anymore. So you got to figure out which one it is. And because of our condition, y of 0 is equal to 1. So that was our initial condition, right? So the y, so there's like two functions here, right? There's a function of x for the plus, another function of x for the minus, but we only want one of those two functions, right? The one that meets the initial value. So keep the plus one. We want the plus one here, right? Because the condition was initial condition was y of 0 equals 1. Okay, so you get y equals square root of 6 plus 3 e to the x minus x over e to the x plus 8. That'd be the y as a function of x. This is the solution. With the plus in front there. We don't have to put the plus, but that'd be it there. That. Okay, so anything on that one? Okay. You see it back up on this one real quick. There's actually a couple solutions there, right? Because when you do this, yeah, you see when I substituted in here, I had 0, 1. Okay. But that could have just been a negative. It could have been just a -1 there as well. If I would have had, say, y of 0 equals -1, okay, then it's, if I have -1 here and a -1 here, it would still have been the same c, right? So there's a couple different things there that would have, if it was y is equals -1 instead, I would have gotten the same curve. I would have gotten the same implicit solution there, okay, but it would have been the wrong half of it, or the other half of it there. So, all right. So anything on that one? That's that one there then. Okay, so that's the end of the exact equations. All right, so done with that now. Next thing here, let's see, is, yeah, now sometimes we're going to look at not exact equations. Okay, so this is actually next section of the book now, section 2.6. But so 2.6 here now. Okay, this is called integrating factors. Okay, so okay, so now the thing about this here, let me just write this down. Well, let me see. Okay, it can make exact multiplying through. I gotta keep writing here. This is like the last section in this chapter. So we're kind of at the top. We're kind of at the most complicated first order ones now, or the this is like the last section here. Or dx. I think it'd be like, okay, it's dx, and I think this is a dy. I think. Yeah. Okay. Provided there's actually provided here, so doesn't always work. There's the whole thing of it. We'll talk about then. Okay. Oh, one more thing here. The U is called an integrating factor. Okay. So we'll go through a couple examples here on this. Okay. Safe to move down from this, or I'll give you, if you're writing this, I'll give you a second to write it because I'm going to run out of room on my screen here. Okay. Okay. Let's scroll down here. So let's look at this one here then. Let's see this differential equation. We're going to try to go through this process. It's not, yeah, so let's go through one. Okay, so let's see. Okay, so let's try it out here then. So basically, what you want to do, it's not exact. You could verify if you did the mixed partial things. It's not exact. Okay, so what you do, next thing to try, it's like next thing to try here then, calculate this thing right here, m sub y minus n sub x over n. Okay, so if I write that down here. Let's see what this is then. Okay, so that would be equal to what here? Well, m sub y, so you take the partial of this with respect to y. Okay, so that would be what? Y squared. Right, y squared, right? That'd be a partial with respect to y squared minus then the partial of this with respect to x is 0, right? Or I'm sorry, y squared. And then divided by y squared here then is equal to 1, like that. Okay, so, and what do we say here? It has to be dependent or x or y only respectively. And this one doesn't depend upon anything here. Okay, so if this depended upon x, you're okay. Okay, but it doesn't depend upon either one, so it's okay. So actually, this is good here. Okay, so then the integrating factor is this. It's u equals e raised to the negative integral, and then it's this thing here, which is it's going to be 1 dx. That's back from this number 1 and number 2 up here. And this. Not for this. No, actually, it's a good question. So far, they've always been negatives in front, but I don't believe, unless I copied something wrong, I don't think there's negatives in front for these. Yeah. Okay. Oh, I turned it into a negative though, didn't I? You're right. My bad. I see what you're saying. Yeah. No. Yeah, you're right. You're right. I got states writing negatives in front from all the other stuff we're doing. Yeah, you're right. Okay, so then this is equal to then what? E to the x. I get e to the x here. Okay. All right, so Okay, so basically here, this is good because it does not depend on y, right? Does not depend on y. So that's good. Okay, so that means this will work because that doesn't depend upon y. Okay. If it depended upon x, it's okay because you can still write this here then. Okay. Now what you do then, you multiply through by this now. Okay, so basically you multiply both sides of the original equation up here. You multiply this one through now by this. Okay, that's the integrating factor. You multiply, so now you multiply your differential equation, the one you're looking for, multiply everything through by this. Okay, and when you do that, it magically becomes exact. Okay, that's the idea. So when you multiply through by that now, okay, right, so what's that becoming? You get like e to the x plus 1/3 y cubed dx plus e to the x y squared dy equals 0, like that. Okay, and now the thing is, this will be an exact equation here now. Okay, I'll just say here is exact. So this is exact here now. Okay. Now at this point, then now you just write this is like your m and your n, or so you do your partial derivatives here now, right? So this is the what f sub x is this one. So now basically once it's exact, now you're back to what we were doing before, right? What we were doing a little bit ago. So now you got your partial respect to x is this one. So then you try to integrate it here, right? So to find f of xy. Oh dear, what's that? Actually this one, another good thing here. This is not a nice integration. If you look at this one here, if I tried the f of x thing here, let me just write this. Don't write this down, but just look at this for a minute. If I try to do this, okay, like this here, if I try to integrate this with respect to x, I treat y like a constant, but I get x e to the x. It's like integration by parts. Okay, not nice. You don't want to do that really. Okay, so what you can do as an alternative, go to the other one first. Okay, because this one's not nice. Okay, maybe that one's hard to get there. So what you can do then, start with the other one first. So f sub y is equal to what? That's e to the x. So one may be easier than the other to do this. Okay, so you start with this one now over here. Okay, now you find f of xy here then. I take the antiderivative with respect to what here now? Well, actually, respect to y. Respect to y here now. Okay. We're just doing these in the other order now, right? We chose to do this one first. Okay, so that becomes what? You get e to the x, or you get basically e to the x times 1/3 y cubed, like that. Okay. Plus some function phi. Now this is of x over here this time. In case you get that. Okay. Now next thing then, now I take the partial of this with respect to x. Okay, and that would be what then? Well, partial respect to x then, how would that go? Well, this is the constant multiplier here, right? So that'd be what? It's just 1/3 y cubed e to the x, okay, plus, and then phi prime of x, okay? But then now what's f of x? F of x is also equal to what? Right, you go back up to here now. Right, so e to the x, what's equal to this thing here? E to the x times x, don't forget the e to the x in front there too, right? E to the x times x plus 1/3 y cubed. Okay, like that. So that's equal to the right side here then. Okay, and then you notice here when you distribute this, right? You distribute this out here then. Okay, so it's still gonna be a mess. But anyway, you distribute this out, you get what? x e to the x. So x e to the x plus 1/3 e to the xy cubed equals 1/3 y cubed e to the x plus 5 prime of x. Now these cancel off over here, right? So those cancel out. And you notice here, now this is only a function of x. Okay, so that's only a function of x here then. Okay, so, and that's because it was exact, right? There was an exact equation up here. Okay, so that worked out. Just be a function of one variable here then. Okay, so anything else so far? Now, last thing to do then, right? We got to figure out now, figure out the phi. Let me switch the sides here of this. Okay, so now we got to find phi of x. And basically here now, this becomes now, yeah, if I write this for just a minute here, it's like we're doing this now. Right, so phi of x equal to this. Okay, and now we're back to, if you remember now from Calc 2, integration by parts you got to do now, right? So, and I think, did we do one earlier this semester here where you do the table, like you can, take derivatives, antiderivatives, right? So you can kind of do this tabular method here. You take derivatives going down here. So that's 1 and 0. Antiderivatives on this column. This is the way to do integration by parts. Okay. So plus and then minus here. Okay. So then phi of x is equal to, so then you multiply these together here. So you get x e to the x minus e to the x, like that. You don't need the plus c on it because we'll have it at the end here. So that is the phi of x is this. Okay, so then finally there we get f of xy is equal to this here. So we got, kind of put this together. So f of xy is equal to, what was it? Yeah, 1/3 e to the xy cubed. Okay, plus the phi of x. Okay, and the phi of x was this part right here then. Like that. And then so the solution then is you set this function out, you set this equal to a constant. Okay, so is the solution here then. And so, and there's no initial condition on this one, I don't think. So so this is the implicit solution here then. Okay. To the original differential equation. And so that's a trip going through that. But anything there now? So basically, it's just what we did a little bit ago, except there's an extra thing at the beginning. You got to multiply through by, figure out the integrating factor and multiply through by it. Okay. Now, if this is still a function of x and y, right? If I go through this here, and this says it depends upon y, or it's a function of x and y, then you're stuck. You're stuck there again. So, but yeah, but anyway. So this is the solution. It's implicit solution. What was our differential equation? Just write it down again. It was x plus 1/3 y cubed. X plus 1/3 y cubed dx plus, I can't even remember what it all is. I'm sorry for scrolling all the time. Plus y squared dy equals 0. All right, and so anything on that one? Going through it? Okay. And this is about the extent of the longness of the problems for this chapter. Okay, so this is about I'd say about the most drawn out they get for the chapter. It's like the end of the chapter, pretty much. So 2.6, integrating factors, right? Okay, see if I have another one here. Let's see. Right, and by the way, what this is kind of saying here, right? I don't know if you remember from Calc 3, we did the implicit differentiation trick. Like if you have this guy right here and you find dy dx, right? Remember we had, don't write this down, but we had dy dx is equal to negative is f of x over f of y, like this. Okay, if you did that here, right, and did that implicit differentiation thing, you would get this here, like this. I think you'd probably get a constant factor of e to the x out here too. It cancel at the end, but anyway, if you did the implicit differentiation thing here, okay, you would, by doing this, okay, and you get something here and something here, and then if you move it around, then it'd be this. Okay, after canceling off maybe an e to the x there, because that integrating factor. So, but anyway, that's how it's all kind of connected. All right. That was number. Did I do that one yet? Okay. All right. Let's try another one here. So let's say we have this one here now. Say xy dx plus 2x squared plus 3y squared minus 20 dy equals 0 is not exact. Okay. Find an integrating factor and then solve. Now just recollect here, this is the m, right? And this is the n. Should have written that somewhere, but I see the m and the n there. Okay, so yeah, so anyway here then, first thing, try to calculate this, right? M sub y minus n sub x over n. So you start by finding this. Okay, so m sub y would be what? X, right? So that's x minus, and then n sub x is and yes, 4x, right? Yeah, make sure I copy my problem down right. Make sure I didn't. Yeah, okay, 4x, okay. And then over n is this whole thing, right? So 2x squared plus 3y squared minus 20, like this. And this is a function of x and y, right? Nothing nice is going to happen here with this. Okay, so it's a function of x and y. This is kind of a dead end, this one here. I'll put like a frown here because it's a function of x and y. That one's a dead end. Okay. Okay, but now let's try the other way. So there's another one to try. Oh, by the way, if it's exact, what if it was exact here? If let's say this was exact, actually, what would this be up here then? If it's exact, say it was exact, actually, right? Then they would equal each other. M sub y would equal n sub x. That'd be 0 up there, right? If it was exact. Okay, so your integrating factor would be like e to the 0, okay, or e to a constant, or say e to the 0 would work. That's like multiplying through by 1, and it wouldn't do anything. You can have integrating factor of 1, but it wouldn't do anything. Okay. But anyway, so I guess if this is 0, if this comes out to be 0 here, you find out it's exact, right? So anyway, now I tried the other way. Now the other expression was this. Basically, problem is here, it's a function of y, right? It's a function of x and y, but that one's no good. Now, you try the other way now. This is the other thing to try. You can see what happens to this. N sub x is what? That's the 4x again. minus m sub y is what, x? Right, m sub y was, it's x, right? M sub y is x, okay, over m. Now I put over m this time. Okay, and this now is nice. I get 3x over xy. It's going to be 3 over y, right? So you get 3 over y here. And it's not a function of x, right? So, so you get 3 over y here is not a function of x. So that's good. Okay, so you get 3 over y here then. Okay. So anything there? Okay, so now the integrating factor, right? So we get u equals, it's e to the integral, basically it's n, one of them was nx minus my over m dy, okay? And that's equal to then, what, e to the, and that was 3 over y. Like this. Okay. And, oh, by the way here, did I assume, we're going to assume y is greater than 0 in this. Somewhere here, I'll just write this down. Assume y is greater than 0 here. Okay. But anyway, we'll see that. We'll be able to get rid of the absolute value then that way. But anyway here, get that. So then, so what this is equal to then, now if you go through this thing, some hand waving here, this is y cubed. Does that make sense? This is going to be y cubed here then. If you do it, because that's the natural log, right? You go through, you get 3 ln, and then you do some exponent stuff. Okay, that's going to be y cubed. Okay, that's assuming y is greater than 0, because I dropped the absolute value off of the, I was able to drop the absolute value off the ln because y is greater than 0. So, okay, so it's got y cubed there. Okay, so that's our integrating factor. So now you multiply through by that. So you go through by this then. So then I take y cubed times xy, and that was dx then, plus, and then y cubed times that other thing, 2x squared plus 3y squared minus 20 dy equals 0. And this will be exact now. Okay. Maybe I'll say here then. Let's say it this way. It doesn't matter. But I'll put the word here. Then this one here is exact. Okay. And maybe I, actually, I think I'll multiply it out here. So that's what, xy to the 4th dx plus, distribute the y through there maybe. I may regret doing that, but I think it'll be easier maybe. 2x squared y cubed plus 3y to the 5th minus 20y cubed. That's all dy there, equals 0. Okay, so anything there so far on that? Okay, so now this is going to be the f of x right here. And this looks like it's pretty easy to integrate, so we'll start with this. So then what, f sub x is equal to xy to the 4th. Okay, and so then that means that I'm going to integrate respect to x here then. So f of xy would equal what? That would be 1/2 x squared y to the 4th. Right, okay. I think that's right. You guys get track of me now. I'm getting kind of dopey. So 1/2 x squared y to the 4th plus a function of y, possibly here. Because if I take the derivative with respect to x partially, I can still get this up here because this would drop off. Okay. Now I take the partial of this with respect to y now. So f sub y is equal to, that would be what, 1/2 x squared? Yeah, okay, go with that. 2x squared y to the third. Yeah, does that seem right? I think that looks, with respect to y. Yeah, okay. Plus, and this is phi prime of y over here. Okay, and now f sub y was what? Ooh, let's see. Well, I guess it'll be okay. F sub y is this, right? Okay, got to end up with a function of y at the end here. So we got 2x squared y cubed plus 3y to the fifth minus 20y cubed equals 2x squared y cubed plus phi prime of y. And fortunately, this x stuff drops off, okay, because it was exact. Okay, so get this here then. So phi prime of y is equal to, I'm switching sides here, 3y to the fifth minus 20y cubed. So then phi of y is equal to, that would be, I think, 1/2 y to the sixth minus 5y to the fourth. So that's this thing up here now. Got that. Okay. So solution here, putting it all together, you got 1/2 x squared y to the fourth plus 1/2 y squared minus 5y to the fourth equals C, right? Is implicit solution. Okay, so what a mess. But that's the so that'd be the solution then to the implicit solution to the differential equation. If I copy, let's see if I copy that right. Anything there in that? So that's the solution to, right, our original, I'll say 2, just kind of be complete here. It's kind of putting this together. Dx, it's, well, I hate to write it all again. Right, so that's the implicit solution to this one. Basically, you could take any first order differential equation and you can always write it in this form, like any first order differential equation. Okay, you can always write it in this form here. But whether it's exact or not, who knows? But yeah, so. But any first order equation, you could write it like this in this form with the dx and the dy and some function here, some function here. Okay, but okay. As another way to write it, you know, if I move this over here, right, move this stuff over to the right and then divide, it's also the same. This is, you can think of like this as well. It's the same thing. I got it right. Wait a minute. I subtracted over, it says minus. I think if you basically divide it through by dx here, and then, yeah, and then I would, it's the same thing as this, right? It's like this differential equation here. So the solution to this one, right, the solution to this differential equation here, okay, is this up here. So, okay. Anyway, anything on that one going through it? Okay. How are we doing here? Okay, 8:03. Any questions on that one? I got one more here to do. I don't know. I'll start on it. Let me start in this last one here. One more to go. Okay, then we're through the section. Okay. But let's try out one more example here, and then this is the last problem for tonight. Okay, I think I can get this done. So let's say we have this one here. Well, maybe it's not a good one to do. It looks very long. Let's see. I think maybe we'll let it go tonight. We'll save this one for now. Okay, on Tuesday, because it won't hurt to do one more next time. But on Tuesday, we're going to do review for tests, right? We got tests next Thursday. So Tuesday will be review for that. So Tuesday review for tests, and then Thursday test. And then following Tuesday, we'll come back and do this last problem here of this. And we'll probably start the next chapter then. So, yeah. In Calc 3.
Like a little shorter
Oh,
because of
because of the time? Yes.